Hello students, my name is Shashank Shekhar. So let us start with the exercise of chemical kinetics. Okay, so let us do the first question. So from the first question says that from the rate expression for the following reaction, determine their order of reaction and dimension of the rate constant. Okay, so we will be given some reactions and their rate expressions, and using the rate expression we have to find the order of the reaction and plus the dimension of the rate constant. Now these are the equations. So there are four equations. The first equation is the 3NO reacts to give N2O, and the rate expression is given as rate is equals to KNO raised to the power 2. So what will be the order of reaction? So if you remember, the order of reaction was something like this. Okay, order of reaction can be written as sum of power of the reactants, sum of the power of the reactant. So if you talk about the overall order of reaction, then it is nothing but sum of power of all the reactants in the rate expression. Okay, in the rate expression. Now, if you look at the first equation that is given, then you would see that it has only one reacting species and which has a power of 2. So the overall order will be for this reaction, it will be 2. So I am writing it as N. So N is equals to 2. Now what about the rate constant? How you will determine it? Simply do the, so if you have the shortcut, so there is a shortcut to do it, or you can just do it manually, right? So I'm telling the long way. So suppose the rate equation is in this way. The rate is equals to K NO raised to the power 2. Now we know what is rate. So it is basically the change in concentration per unit time. So the concentration is represented by mole per liter and per unit time, so per second. So for K we have to determine it, and again we have the concentration term which has a power of 2. So concentration term is represented with the help of mole per liter. So if you just square it, that would give you mole square per liter square. Is it correct? You can just think over it. Then K will be finally, if you bring this thing here, that would give you mole 1 minus 2 liter minus 1 plus 2, and we have per second. Okay, so the good way to write the unit of anything is to write those terms first which has a positive power. So this mole will have a negative power. Okay, so we will write it at on the later side, but this liter will have a positive power, that is plus 1. Okay, so I'm just writing it L. I'm not writing anything at the power, so it means that it is 1. Similarly for mole it will be inverse. Okay, so it is liter mole inverse, and then we have per second. So this will be the unit of rate constant. Is it okay? Okay, so now next thing, how we'll do it in the shortcut way. So there is a simple formula for that. It is given as mole. So suppose N is the order of reaction, then 1 minus N, and liter is written as N minus 1, and we have a per second. So this is the shortcut to do it. So if you just put this powers here, you can do it easily, right? So if you put N is equals to 2, then 1 minus 2 will give you minus 1. N is equals to 2 here will give you liter 1. I'm writing it here, and per second. Now let us use this formula for the rest of the questions. Okay, so just I'm writing it here on the main page, which is this one. So mole 1 minus N liter N minus 1 and per second. Okay, so we'll use this formula for all the remaining questions. So we have find this as mole, okay, sorry, liter mole inverse and per second, right? Now second equation, what is the second equation? So the second equation is H2O2 plus 3I minus plus 2H plus, which gives us 2H2O and I3 minus, and the rate expression is written as rate is equals to K H2O2 raised to the power 1, and I minus is also raised to the power 1. So what is the order of reaction? So we have to add the power of the reactant, we have to sum it. So H2O2 has a power of 1 and I minus has a power of 1. If you just add 1 plus 1, it will give you 2. So this is the order of reaction. Now let us find the rate constant. So we will use this formula. So mole. Let me do it on another page. So I'm doing it for the second, right? So n is equals to 2. We find n is equals to 2. So we will just use this formula. I have done it earlier also. It was n equals to 2 for the previous question also, but I'm doing it again here. 2 minus 1 second inverse. Again, since it looks good to put the positive at the first, so I'm putting this one first, then mole, inverse, and per second. So this will have the same unit of the rate constant. What about the third question? What is the order of the third question? You can see here that there is a very good lesson for this chapter, that order can be fractional, right? So here you can see that this reactant is raised to the power 3 by 2, which gives us that order as 3 by 2. So order can be fractional, right? Order can be fractional. Now, what about this unit of rate constant? So again, we'll use the formula, which is mole 1 minus n, liter n minus 1, and per second. So if you put n is equals to 3 by 2, so mole will be 1 minus 3 by 2, liter will be 3 by 2 minus 1, and per second. If you just subtract it, this will give you mole will be minus 1 by 2, liter will be plus 1 by 2, and per second. Is it correct? 1 minus 3 by 2 is 1 by 2, but since 3 by 2 is greater, so we'll take a negative sign. Similarly for liter, and then per second. So this is your answer. L 1 by 2, mole minus 1 by 2, and per second. Now next question. So rate is equals to C2H5Cl. What will be the order of reaction? So there is only one reactant which has a power of 1. So n will be equals to 1, isn't it? Right? Now about the order of the rate constant unit. So mole 1 minus n. So we have n is equals to 1. So it will be 0. Then liter n minus 1, again 1 minus 1, and then per second. So this will finally give you rate constant unit as per second. So this will be per second. Are all these questions clear? Okay. So there was a simpler question. Now let us move to the next question. So this is a solution. If you want, you can say, just passing the slides. You can just see it when the video gets uploaded. Okay. To find difficulty. Okay. Now next question. So the question says that we are given a hypothetical reaction, that is 2a plus b gives us a to b, and the rate is given as a b square, and the rate constant is also mentioned 2.0 into 10 to the power minus 6. What we have to calculate? So we have to calculate the initial rate of reaction. Okay, initial rate of reaction when a is equals to 0.1 and b is equals to 0.2, right? So this is the first question. Second is, calculate the rate of reaction after a is reduced to 0.06. Okay, so let us do this question. So first case says that we have to find it for the initial rate. So at initial at t is equals to 0, a is 0.1 and b is 0.2. So a is 0.1 mole per liter per second and b is 0.2 mole per liter per second. What about the rate constant? That is k is equals to 2 into 10 to the power minus 6, mole minus 2 and liter 2 s minus 1. So k is equals to 2 into 10 to the power minus 6, mole minus 2, liter plus 2, and per second. Also, we are given the rate expression R is equals to KAB square. Now all the values are given. You don't have to worry about anything. So at t is equals to 0, that is at the initial phase, we have the rate as, so if you put the value of k, it is 2 into 10 to the power minus 6. Okay. If you put the value of A, concentration of A, it is 0.1. For B, it is 0.2 raised to the power 2. Clear? So 2 to the 4. Now this will be off. This will be gone. So this will be 10 to the power minus 2. If we just expand it, first let us just expand it. Okay. 2 into 10 to the power minus 6. This is just 10 to the power minus 1. And this is 2 into 10 to the power minus 1. Okay. Now we can do it easily. So 2 to the 4. And 10 to the power minus 6, 10 to the power minus 1, 10 to the power minus 1. This will be minus 4. Okay. Yeah. Okay. So minus 6, minus 1, minus 2. So total will be 6 minus 3. That will be minus 9. So this will be our rate. Okay. So this is our first question. Now second question is, calculate the rate of the reaction after A is reduced to 0.06. Okay. So initial concentration of A was 0.01. Okay. I'm just writing it. A naught is equals to 0.1. And at time t, suppose it is reduced to 0.06. Now what is the change in concentration of A? Change in concentration of A is equals to 0.1 minus 0.06. That would give you 0.04. Now we can say that 0.04 mole of A has reacted. Okay. So let's write this equation and you can get a more clear picture. Okay, you are saying that that 0.04 mole of A has reacted. Now here you can see that 2 moles of A reacts with, so it reacts with 1 mole of B, or we can say 1 mole of A reacts with 1/2 mole of B. Now how many moles of A has reacted here? 0.04. So 0.04 mole of A will react with 0.04/2 mole of B, which is equals to 0.02 mole of B. So this much mole of B has already reacted. What was the initial concentration? If you remember, it is 0.2. So what is the final concentration? So at time t, it will be 0.2 minus 0.02. You will simply subtract it because this much has reacted. So that will give you 10 minus 2, 8, 1 and 0.18. Is it clear? So this is clear. How we have find this? Okay, this is mole per liter. This is also mole per liter. Now again we have the concentration of A at time t and concentration of B at time t. We have to find the rate. So rate is equals to K A B square, or K was 2 into 10 to the power minus 6. A is 0.06 and B is 0.18. What will be the answer? So 6 to the 12. I'm just expanding it again so that we can make the calculation easier. 6 into 10 to the power minus 2. 18 into 10 to the power minus 2. Now 18 to the 36 and 36 6 ja 6 6 ja 36, 6 3 ja 18, 18 3 21. And this is minus 6 minus 2 minus 2. 10 to the power minus 10. Now if you just write it in proper scientific notation, this point will go here and the power will be reduced. Sorry, power will be increased by plus 2. That would give you 10 to the power minus 8. So this will be rate. So it will be mole per liter per second. Clear? So in this way, we will solve this question. Easy? Okay. So here we have done the same thing. See, now one mistake I have done, that if we just square 0.2, it will give you 0.4 into, sorry, it will give you 4 into 10 to the power minus 2, and I have taken it as 2 into 10 to the power minus 2. Okay, so that will give it 8 and not 4. Okay, so you can just improve it. And this one was 0.08. We find it similar. This was 0.04. It was already given. And finally, it would give you 3.89. Okay, so if I have done some calculation mistake, you can just improve it. So the calculation mistake was that the rate expression is this square. So I'm not taking the square of this, right? So you just put the square of this, then you will find this 3.89. Okay, so this mistake I've done. Clear? Next question. The decomposition of NH3 on platinum surface is 0. Order reaction. Now, what are the rates production of N2 and H2? So first of all, let us write the decomposition reaction. So NH3, it will decompose to N2 and H2, right? Now 1 mole of N, so I'm writing it as 1 by 2, and 3 moles of H, so I'm writing it as 3 by 2 H2. What we have to find? We have to find the rate of production of N2. The rate of production of N2. How you will find it? Okay, so first of all, we know that for how can we write the rate expression? So it is written as rate is equals to K. What is the reactant? NH3. Okay, NH3 raised to the power N. But it is given that N is equals to 0. So NH3 raised to the power 0 will be 1. So rate will be simply equals to K. And this value is given as 2.5 into 10 to the power minus 4 mole per liter per second. Clear? Okay. So this thing is given. Now we know that rate is equals to 1 by coefficient. So we have seen this 1 by coefficient. So suppose I'm writing it for N2. So 1 by coefficient is 1 by 1 by 2 and dA by dt, right? Change in concentration of A by time. And now that is the rate of production. Okay. If I'm writing it for N2, since it is a product, so it will have a positive sign, and N2 dN2 by dt. Now this is our rate of production of N2, right? Similarly, if you write it for this thing, then it will be 1 by 3 by 2 and again dH2 by dt. Now equate each of this term individually with rate and you will get your rate of production of N2 and H2. Is it clear? So first of all, let us do it for N2. So writing it here 2.5. So rate value was 2.5 into 10 to the power minus 4. And this was equals to 1 by 1 by 2 d N2 by dt. And if we just bring this thing here, so 2 will go here, 1 by 2 will go here. And this will finally give you how much? 2 1 is 2, 2 is 4, 2 5 is 10. Bring this here, that is 1.25 into 10 to the power minus 4. So this will be rate of production of N2. So what will be the unit here? So we have concentration of the on the upside, so mole per liter, and time on the downside. So per second. Easy? Okay. If I just 10 to the 4 or 5, 2 in the 2. Yes, this is correct. What about the second one? So again, we will equate this individually with the H2. So 1 by 3 by 2 dH2 by dt. Or we can write it as dH2 by dt is equals to 2.5 into 3 by 2 into 10 to the power minus 4. So we have 2.5 by 2 as 1.25. It is multiplied by 3. 3 5 is 15, 3 2 is 6 1 7, and 3 1 is 3. This will again have a unit of mole per liter per second. Clear? So in this way, we'll do this question. Simple. Now let us look at the solution. Okay, so I've done the same thing since we are not interested in this. So I have not written this. So if you just do it with this one, that will give you 7.5. Okay, and this is 2.5. Right. So okay, so let me have a look at this. Okay. So the thing they have done is that they have taken this equation, right? And I have taken different equation. So you can do it in the either way. Okay, so both are correct. You don't have any problem with each of this. So the answer is coming different. So this should not be the case, right? This should not be the case. So we'll come back to this. What are the decomposition of NH3 is? What are the rates of production of N2? So I think the equation should be given along with this question. Okay, so then only we will derive according to the question, right? Okay. So let us put this question on hold. So they have done the same thing on all. The thing is that only they have taken the different equation, right? If we just divide this equation by 2, all of this equation by 2, this will be 1, this will be 1 by 2, and this will be 3 by 2. Okay. Next question. The decomposition of dimethyl ether leads to the formation of CH4, H2, and CO, and the reaction rate is this. Okay. Now, the rate of reaction is followed by increase in pressure in a closed vessel. So the rate can be also expressed in terms of partial pressure. So what they are saying is since this all of this are CH4, H2, and CO, all of these are gases. So what do we do if we just leave the concentration and try to express in terms of pressure? Then we can do the same thing. Okay, right? So in this way we can write it. So we're taking the pressure of CH3, OCH3. Now, if the pressure is measured in time bar and time in minutes, then what are the units of rate and rate constant, right? So we have to find the unit of rate and rate constant. So what about rate? What will the unit of rate say? So rate is change in concentration per unit time if it is about concentration. But if it is about pressure, that it is change in pressure per unit time. Okay, so if I'm writing the rate, it is change in pressure per unit time. Clear? So change in pressure, here pressure is a unit of bar, so I'm writing it as bar. Per unit time, a time is in minute. So that will give you bar per minute. Clear? Very easy to understand. Now what about the unit of K? Now let us look at the unit of K. So rate is given as K P CH3 OCH3. It is 3 by 2. Now we have already find the unit of rate. It is bar per minute. K, and this is simply bar. This is 3 by 2. Hence we can write K is equals to bar. So it is 1, it is 3 by 2, 1 minus 3 by 2, and this is per minute. So 1 minus 3 by 2 will give you how much? The 2 minus 3, that is minus 1 by 2, and this will be per minute. So this will be our unit. Okay, this will be our unit. You can just look at it how we have done it. Just analyze this pressure term, and you will find that this is very rationalized. Now let us look at the answer. Solution of this question. So it is bar minus 1 by 2 per minute, and it is bar per minute. Okay, so we have done it correctly. Next, we have mentioned the factor that affect the rate of reaction. So what are those? If you remember, so this is just a theoretical question. I am putting the answer in front of you. Okay, so the factors are concentration of reactant, of course, temperature, and presence of catalyst. So this concentration of reactant comes from the rate expression. Temperature, of course, it is important. This comes from Arrhenius equation. And presence of catalyst. So we have seen that it decreases the activation energy for the given reaction. Next is a reaction is second order with respect to a reactant. Okay. Now, how is the rate of reaction affected if the concentration of the reactant is doubled? So we are saying that the rate is second order with respect to a reactant. Suppose I am taking the reactant as R, so this will be square. Now, how is the rate of reaction affected if the concentration is doubled? So suppose that initially we take it as R. Okay, so the concentration at R naught is taken as R. So rate will be directly proportional to concentration of R raised to the power 2. Now suppose after time t, this concentration is doubled. So 2R, suppose is rate 1 and this is rate 2, right? So this is now 2R and again squared. So that will give you rate 4R square. Suppose this is first equation, this is second equation. Now 1 divided by 2, I'm just dividing it. So 1 by 2 will give you rate 1 by rate 2. This will give you rate square by 4R. Okay, so you can do this thing. You don't have to worry about it. So how you have done it? So suppose if you just remove this proportionality constant, you will get a constant K. Okay, and now if you similarly if you do it for second, now 1 divided by 2, the proportionality constant will be cancelled out, K and K, and this will give you this equation. Now it is asked that how is the rate of reaction affected? So this is the initial rate of reaction. You can see that if you just square it, the new rate of reaction, that is rate 2, is 4 times the initial rate of reaction. Okay, clear? You get it? Okay. Now, if it is reduced to half, so initially it is R, and next case it is reduced to R by 2. It is half, so it is 1 by 2 or half. Clear? Now for the first case, again I'm writing in the same way. You also do it by yourself. It is R square. For the second case, it is R by 2 square. Clear? Divide both of this equation. This will be rate 1 divided by rate 2. So this and this will be cancelled out. That will give you 1 by 1 by 4 or 4. Now what will the rate of reaction? So if you just cross multiply it, you will get it as 1 by 4 rate 2. So we can say that after halving the rate of halving the concentration, you get 1 by 4th of the initial rate, right? Let us look at the answer. So it is increased 4 times and this is reduced to 1 by 4 times. Okay, no problem. Next question. What is the effect of temperature on the rate of a reaction? How can this effect of temperature on a rate of reaction can be represented quantitatively? So this is theoretical question. I'm directly putting you the answer. Okay, so this is the saying, means for general it is said that the rate of reaction is nearly doubled. Okay, so if you just increase the temperature of rate of a reaction by 10 degrees Celsius, then the rate is nearly doubled. So this is a statement, general statement. And if you talk about the appropriate relation, that it is given by the Arrhenius equation, and it is K is equals to AE to the power minus, AE to the power minus EA by RT. So this is the Arrhenius equation, right? Where A is the pre-exponential factor, E is the activation energy, R is the gas constant, T is the temperature in Kelvin, and K is the rate constant. Okay, clear? Now, same thing is mentioned here. Next is, we are given a pseudo first order reaction in water. The following results were obtained. Okay, so we are given the pseudo first order reaction, and these are the results that we are given. So initially the concentration at time t is equals to 0 to 0.55 at 30 seconds. So it is given seconds. It is 0.31 mole per liter. 60 seconds it is 0.17 mole per liter. 90 seconds 0.085 mole per liter. So what we have to do, we have to calculate the average rate of reaction between the time interval of 30 to 60. Okay, 30 to 60. How we'll do it? Say, what is the formula for finding this average rate of reaction? It is basically the change in concentration by change in time. So at two instances we have to do it, at 30 and at 60. So at 30 seconds, the rate is given as, the concentration is given as 0.31. And at 60 seconds it is 0.085, 0.17. Now what about the average rate of reaction? It is change in concentration by change in time. This is the formula, simple. So we'll do it with a negative sign. Since we are talking about reactant, okay, so we'll put a negative sign to maintain the sign convention, because rate cannot be negative. So 0.17 minus 0.31. This is the change in concentration of reactant, and change in time is 60 minus 30, and this again with the negative sign. What will the answer? 11 minus 7, 4. 2 minus 1, 1. 0.14. And this is 60 minus 30. So 0.4 minus 30. If you just calculate it, you will get it as 0.14 divided by 30. 0.00466. Or we can write it as 4.67 into 10 to the power minus 3. If you just calculate it, you will get this one. Okay. Is it clear? Okay. Let us look at the solution. So we've done the same thing. Change in concentration by change in time, 0.14 by 30, that is 4.67 into 10 to the power minus 3. So we have rounded it to up till second decimal. So we have a second question also. I think it is not mentioned here. So what we have to find? We have to find the what we have to find? We have to find the rate constant. Okay, we have to find the rate constant. How we're doing it? So since it is a first order reaction, although it is pseudo, but it is a first order reaction only. So we'll take the rate law of the first law. Okay, we put the values, we get the time. Similarly, for 60 seconds, we get the time, and then we calculated the average rate of reaction. And we took it up for 90 seconds also. So at 3 instances we do it, and we get the time, we get the rate constant at 3 different rate constant. Finally, we take the average of it. So this is your final answer. Next is a reaction is first order in A and second order in B. Okay, first order in A and second order in B. So what we have to see, we have to write the differential rate equation first of all, and how is the rate affected on increasing the concentration of B 3 times? Second question. And third question is how is the rate affected if we double both the concentration of A and B? Let us solve this question. So first of all, what is differential rate of reaction? Does anyone remember how we write it? Okay, so it is written in this way. Change in concentration. It is first order in terms of A. Suppose I am representing the reactant with R minus dr by dt. This is our differential form. Okay, and minus dr by dt. And this one is first order, right? A raised to the power 1 and B is raised to the power 2. So this will be your differential rate law. First question done. Second is how is the rate affected on increasing the concentration B 3 times? So if you just write it in simple terms, the rate is equals to Ka B square. So initially it is said that suppose first case is that it is B naught is equals to B. Now suppose after we do it as B initial, B final. Just take it as 3B. Okay, 3 times. Now let us write it for the first case, it as rate 1. Okay, rate 1. Is this cool? Okay. Now what about rate 2? Concentration of A is kept constant. You don't have to worry about it. What about B? It is 3 times now. Just take the square of this. Just find out, this will give you rate is equal to, rate 2 is equal to K, this is 9 A P. Got it? Now divide both of this. So rate 1 by rate 2 will give you Ka B square 9 Ka B square. Finally, the rate will be now 9 times the initial case. Clear? Simple? Okay. Now third question, how is the rate affected if we double the concentration of both? So initially it is Ka B square. Now we have doubled the concentration of both. A is 2A and B is also 2A, 2B. So rate 2 can be written as how much? K 2A and 2B. Divide both of this. Rate 1 by rate 2. This will give you K A B square. This is 2 for the 8 K A B square. So this will be cancelled out. You will get rate is now 8 times the initial value. Got it? So this is our first answer. Second, it is 9 times. Okay, so you find out, and this is 8 times. Clear? Okay, so we have done this question. Next question. So next question we have, so in the reaction between A and B, the reaction between A and B, the initial rate of reaction was measured for different initial concentration of A and B. Okay, so what they have done, they have taken a different initial rate, different initial concentration of A and B, and they have calculated the initial rate of reaction at different concentration. 3 concentration they have taken. First is A is taken as 0.2 and 0.3. This will give you this value. Second is 0.2 and 0.1, this value, and 0.4, 0.05, this value. What we have to do? We have to find the order of the reaction. Okay, you have to find the order of the reaction. How will find it? Say, so we will simply use the rate expression. So for the first case, suppose I am taking that with respect to A. Okay, with respect to A, the rate is X order. Okay, with respect to A, rate is X order. And similarly, with respect to B, the rate is Y order, isn't it? Is it clear? Okay. Now, let us write the rate expression at 3 times for the 3 cases. So first case, if I'm writing it as, suppose I'm writing it as R1. A concentration is how much? 0.2 raised to the power X, and B concentration is 0.3 raised to the power Y. First case. Second case is 0.2 and 0.1. So 0.2 and 0.1. So the rate 1, I'm writing the value of rate 1 also. It is 5 into 10 to the power minus 5. So this is 5 into 10 to the power minus 5. And this one is also 5 into 10 to the power minus 5. Actually, it is 5.07. This is X and this is 0.1Y. Now divide both of these equations. Okay, let's divide both of this equation. This and this will be cancelled out. This will be cancelled out. Now we will get it as 0.3y is equals to 0.1y. You will get this. Okay. So when these both terms can be equal, so there can be only one case. If we take y is equals to 0, so this will be 1 and this will be 1. Okay. So in that case only, if y is equals to 0, then only we can say that it is a valid equation. So this means that the value of y is 0. Okay. Value of y is 0. Now, what will the value of x? For this, you can take any of the equation. Suppose I am taking this 5.07 into 10 to the power minus 5. 0.2, this is the this is x, and this is 0, so that will give you 1. So I'm not putting that value. Take the log of it. The log of 5.07 into 10 to the power minus 5, and if you take the log of this is x, log 0.2. Just find it for x, you will get the final answer. Or you can do it in the different way also. Just take this equation and then you can find it. Okay, so I think this is suitable finding it. Okay, this is clear. Okay, second question. Sorry, next question. So if you look at the solution, this okay, good. This is 0. Take the log of it, or they have done in a different way as I have told. See, they have again taken 2 different equations, put the values, and then they find it as approximately how much? 1.5. Okay, so you can do it in the either way. You can use the single equation or you can use 2 equations. Okay. Next question. The following results have been obtained during the kinetic study of the reaction. So we have a reaction that is 2a plus b gives us c plus d, and here is the kinetic study of that. So this study says that so if you have a concentration of A at different values, 0.1, 0.3, 0.3, 0.4, and B as this, and this, and initial rate is also given. Okay, so what we have to do, determine the rate law and the rate constant. Okay, rate law and the rate constant. How will you solve it? Simple. Just write the rate expression for any of these two, such that out of A and B, one concentration is remain same. Suppose I am taking 2 and 3. Okay, so in 2 and 3, the concentration of A is kept same and B is changed. So we will take this type of equation. Okay, if you write it for the second, suppose I am writing for the second, R2, K value is 7.2 into 10 to the power minus 2, and I'm telling that with respect to A it is X order, and with respect to B it is Y order. So rate for second condition can be written as 0.3x and 0.2y. Similarly, for three conditions, 0.3 and 0.4. Okay, 0.3 and 0.4. What about the value of rate? It is 2.88 into 10 to the power minus 1. Now divide both of these equations. Okay, just divide it. This will be cancelled out. Clear? What about this? I think I have done something wrong here. So this was the value of rate and not the rate constant. Okay, so I put this value here, so I have to write it here. So 7.2 into 10 to the power minus 2, and this is 2.88 into 10 to the power minus 1, and this is the rate constant. Suppose I am taking the rate constant as K, so it will be equal. It does not depend upon concentration. So this will be cancelled out, right? So this will be 0.2 by 0.4 y. What about this? If we just divide it, 0.072, it is divided with 0.288. So that will give you 0.25. 0.25, or just remove this. So 2 by 4 will give you 0.5. Why? 0. So you can write this 0.25 as 0.5 square, isn't it? Now if you equate this, you will get the value of y as 2. Clear? Got it? So we got this as 2. Now we have to find it for x also. Okay, you have to find it for x also. I will do it. So again, take two equations. Suppose I'm taking two such equations in which the other is cancelled. So I'm taking it 1 and 4. So rate 1 is equals to, the rate 1 value I'm writing it directly. It is 6 into 10 to the power minus 3. Right? K 0.1 raised to the power x and 0.1 raised to the power y. So y value of evaluated, it is 2. For second, for the fourth, it is 0.4, 0.1, 2.4 into 10 to the power minus 2. K 0.4, 0.1, 0.4 and 0.1. Now divide both of these again. Cancel out. Cancel. What about this? Six 4 the 24. Okay. This and this will be cancelled. We'll get it as 1 by 4. Clear? And this will be also 1 by 4 x. Obviously, x is equals to 1. So we can write that y is equals to 2 and x is equals to 1. What about the rate constant? suppose I'm taking this equation. Okay, I'm taking the first one. So first one is 6 into 10 to the power minus 3. K we have to find. This is 0.1. It has a power of 1. This is 0.1. It has a power of 2. So K will be equals to 6 into 10 to the power minus 3 and 0.1 cube. Okay, 0.1 cube. Else we can write it as 10 to the power minus 3. So this will give you 6. What will be the unit of rate constant? Very interesting question, right? Just don't leave it, okay, without writing the unit. It is very important. So we have devised a formula for that. It is mole 1 minus n. Okay, it is mole 1 minus n. What is n here? Order of the reaction. So first with respect to A, 2 with respect to B. 2 plus 1, 3. So 1 minus 3, liter, 3 minus 1, and mole, second inverse. This will give you liter square per mole square and per second. So liter square per mole square and per second. So this is the final answer. They have done the same thing, written 4 equations. X is equals to 1. Okay. Y is equals to 2, I think. Okay, so they've not calculated for Y, so you will get it as 2. We have seen this, okay. And this is 6 liter. Liter square per mole square, minute inverse. So this will be minute inverse. If you look at the data, not second inverse, it will be minute inverse. See, it is written meter inverse, right? So just look at this, okay. Be keen about it. Next question. So this is our last question. We will do the rest of it in the next class. So this question says that the reaction between A and B is a first order reaction with respect to A and zero order reaction with respect to B. So we have to fill this blank, right? First is given completely. Second is saying that, if I'm directly writing the rate expression for the second. So R2 is equals to, so R2 value is given as 4 into 10 to the power minus 2. 4 into 10 to the power minus 2, and this will be equals to K, that is our rate constant. And concentration A is not given. Suppose I'm taking it as this only, A1, and with respect to A it is zero order, and with respect to B it is, with respect to A it is first order, and with respect to B it is zero order. You're right. B concentration is given, so it is 0.2. What is the problem here? We don't have the value of K. How we can find it? Say, what is the given set of data that is appropriate to find K? So the first set of data is very appropriate because all the values are given except K. So first of all, we'll find K. So for the first case, if I'm writing it is, so rate 1 is equals to 2 into 10 to the power minus 2, 0.1 raised to the power 1, B, so 0.1 raised to the power 1, this K, and 0.1 for B raised to the power 0. So K will be equals to 2 into 10 to the power minus 2. So this can be written as 10 to the power minus 1 or 2 into 10 to the power minus 1. So this is our rate constant, right? Just put this value here. The rate constant value is 2 into 10 to the power minus 1. Okay. A, we have to find it. B is at 0. So this will give you 1. Finally, we can write A for second, I think. Yeah, we have to calculate for second now. So second. This will be what? 4 into 10 to the power minus 2 by 2 into 10 to the power minus 1. 2 to the 4. 2 into 10 to the power minus 1. This will be your answer, okay? What will be the unit of this? Mole per liter. What about this? Just let us try it. So This is not given. So I'm writing it as rate 3. K value, we have find it 2 into 10 to the power minus 1. With respect to A, it is 0.40. With respect to it is 1. And with respect to B, it is 0. Okay. So that will give you 2 into 10 to the power minus 1. So I'm writing it in expanded form. Okay, clear? Mole per liter per second. This is the unit of rate. This is 0. Sorry, 1. Okay. What about the fourth one? Again, we have to find it for A. The rate is given as 2 into 10 to the power minus 2. K value 2 into 10 to the power minus 1. A we have to find for fourth. B is 0, so I'm not writing it again and again. So A4 will be equals to 2 into 10 to the power minus 2 by 2 into 10 to the power minus 1. So this will give you 10 to the power minus 1. Final answer, mole per liter. Clear? Okay, now let us look at the solution. So this is the thing. This is 0.2. This is also 0.2. We find it. We found it. This is 0.08, 0.1, and okay. So with this, I end my lecture. So we'll do the rest of the exercise, that is 13, 14, and the rest of the one in the next class. Okay. Thank you.